Tēnā koutou katoa, kia ora, welcome to the 5th Science Seminar. Just before, a couple of things to quickly go through with you. I'm Brodie Young, I'm the manager of the Environmental Science and Hazards section, one of the 3 sections we have in the science group. I'll introduce the speaker in a minute, but just bear with me for a short while. Just stuff from the managers of this facility. In the event of an earthquake or other disaster, obviously remain calm and remain in the room, just protecting yourself, remain seated. Key thing is not to avoid the temptation to look out the window, just face away from the glass. That's one of the hazards that they've identified. So yeah, exits, obviously the door you came in, immediately to your left, it's marked as an exit, that's the stairwell, and there's an exit at the front of the room. So yeah, go down to the ground, and the meeting area is out in the car park out here. Toilets, men's and women's just there, cup of tea, please help yourself. So I'd like to introduce Justin Cope. Justin is the team leader of the Coastal and Hazards team in our section. Justin has a Master of Science degree in Honours from Canterbury, a Resource Management degree from Lincoln, and is an adjunct to the Geography department at Canterbury. I asked him what you get if you're an adjunct, because I thought I might borrow his library card or something, but which, for those of you who covet such things, access to the university library can be quite good, but apparently he hasn't got one, so I don't know what you get for being an adjunct, but he does have input into the program in physical geography at the university. In a couple of months' time, Justin will have been here 20 years, which is a milestone, but I mention it more for the fact that, that as you'll see from the presentation, long-term records of sea level rise and is important, and Justin's certainly been able to keep an eye on things in the last 2 decades. So, yeah, over to you, Justin. And just before we start, can I thank everyone? It's such a great turnout. It's one of the better turnouts we've had. So, thank you very much for making the time. I'm sure you'll find it worthwhile. Thank you.
Thanks, Brodie. Good afternoon, everybody. Yeah, great turnout. I've always found over my, thanks for reminding me, 20 years or so at Environment Canterbury, if you want a public meeting about anything coastal, go for the doom and gloom angle. It packs them in every time. I guess everyone's knowledge of sea level rise is a little bit varied. So I'm hopefully by the end of the day, I'm going to give you a little bit of an appreciation on what we hear a lot about global sea level, and so that's what's happening on a throughout the world on a global scale. But in reality, what we're really concerned about, particularly as environmental managers, is what's happening on a local scale. So I'm going to start out global, because you hear in the news, IPCC have put out a new report that says the global sea level is going to be this much. But what we're really interested in, is what's happening locally, what's happening to our own coastal water bodies, our estuaries, our rivers, and our coastline. So I will start off a little bit about what's causing sea level rise, have a look a little bit about what's happened historically, and what has happened, what the most recent, I guess, science consensus predictions of future sea level are, and then, like I said, have a look at some more local stuff. Just before I start, they say that imitation is the greatest form of flattery, and it's fair to say that today's talk flatters the hell out of a couple of pieces of work. The Parliamentary Commissioner for the Environment, I think 2014, I think, put out a really good science summary report, and that's on the website if you wanted to have a look at that, on the Parliamentary Commissioners for the Environment website. And Deirdre Hart from the Geography Department of the University of Canterbury in 2013 gave a really, really good lecture, a what if lecture. It was a series of lectures that the university put on about what's happening with Christchurch's sea level rise. So you can Google that too and just see how much of my talk is original. We can't really talk much about sea level rise without touching a little bit on climate science. The climate science is kind of a massively complex and vast interdisciplinary topic, well beyond my meagre understanding of things. But one of the main aspects of climate change, and we know it is, and we can measure it, is sea level rise. So I'm going to indulge for a couple of minutes in a little bit of history. Now, the old 18th century gentlemen scientists, when they were doing their grand tours of the Swiss Alps, came across things that looked a bit like this. They called them, what did they call them? Outliers. And these were large boulders of a completely different rock type than what they were situated near. So they had to think about it. What could have put them there? Obviously, water was probably not an option. You know, no real water-based process, fluvial-based processes could get them there. So they figured that, you know, they must have been put there by ice, and obviously that was compounded by identifying, you know, ex-glacial features like moraines, striations, and U-shaped valleys. So really, what they discovered and what they deduced, that the Earth's climate was obviously a lot different in the past. This isn't a pub quiz, but these are some of the early players in climate science. Some interesting figures. This chap here is really interesting. His name's James Kroll, and he was a Scottish scientist, and he was self-taught. He was the first to figure out that, you know, the variations in the Earth's orbit caused ice ages. He's an interesting guy, and he was a janitor at one of the universities in Glasgow, I think. And every night when he was supposed to be cleaning, he brought his brother-in-law with him to work with him. So while his brother-in-law did his cleaning job, he went to the library and read books and educated himself. Carrying on from his works, you may have heard of things called Milankovitch cycles. This is Milutin Milankovitch. He was a Serbian geophysicist, and he took some of James Kroll's work and further calculated the link between the Earth's orbit and ice ages. Mystery Scientist C, John Tyndall, he was an Irish physicist, and apart from looking like he needs a good laugh, was one of the first to describe the effects of greenhouse gases, mainly the ability of these greenhouse gases to absorb heat in the atmosphere. Mr. D was a Swedish chemist, Svante Arrhenius, and he was well ahead of his time. He drew the link between, this is about in the 1880s, he drew the link between the greenhouse effect and the burning of fossil fuels. And being from Sweden, he didn't think that was such a bad thing, that the Earth was warming. He also discovered the importance of feedback loops, those positive feedback loops and negative feedback loops, which are important when you're talking about climate change. So these feedbacks, positive feedbacks, are kind of the accelerators of climate change, global warming, and negative feedback loops are the brakes, if you like, to use that same analogy. So, for example, in a warming atmosphere produces more evaporation from the oceans, so more water vapour. Water vapour is a greenhouse gas, so you get more water vapour is a greenhouse gas, which causes more warming, therefore more evaporation. And finally, Mr. E is a British steam engineer, ironically, who contributed to the climate science considerably by finding the link, or demonstrating the link between atmospheric carbon dioxide and the warming atmosphere. So we're skipping ahead a fair way in terms of scientific technology. So in those preceding centuries, from those old fellas who were doing their thing, obviously techniques like satellite imagery have really enhanced our knowledge of what's happening to the Earth's climate. And just as an example here, here's an extent of the summer polar sea ice from 1979 compared to 2007. As you can see, considerable change in the coverage of that sea ice, and this kind of goes to demonstrate a little bit of what I was talking about before about these positive feedbacks. It provides us a good example. Obviously, we've got a lot of white here. A white surface reflects a lot of the solar radiation. If you lose that white, you end up with a lot more dark ocean that obviously absorbs more of the sun's heat, raising the temperature of the ocean, causing more of this to melt. So that's another example of positive feedback. So 3 significant processes going on. I'm going to go really quickly over these. Carbon dioxide in the atmosphere is increasing, resulting in global mean temperature rising, which has the effect of increasing sea levels. Atmospheric carbon dioxide was really started being measured in earnest physically by Charles Keeling. Started about, no relation I don't think, Chris, in the late 50s. He measured CO2 in Hawaii quite fastidiously. You'll notice that the sawtooth pattern, obviously the first thing to notice is the trending upwards of carbon dioxide, but also the sawtooth pattern, and that's also known as, colloquially known as the earth breathing. So that's particularly we're talking about the northern hemisphere, that's the uptake of oxygen by forests during the most productive growing seasons in the spring and summer, and then obviously so it drops the carbon dioxide, and then an increase during the winter where those trees lose their leaves. Also the decomposition of those leaves leads to increase in carbon dioxide as well. Ice core data. Bubbles of air are trapped in polar ice. Taking cores of those, scientists are able to go back millions and millions of years. But if we just look at what's happened over the last century or so using the ice core data, and then adding on Keeling's Hawaiian data, so you see that that carbon dioxide concentrations has really taken off in the last 50 or 60 years. And alongside that, global mean surface temperatures have been increasing. These jump around a lot more than obviously the carbon dioxide. So there's not obviously a one-for-one link, but these are this just demonstrates a little bit more variability in climate cycles. But obviously there's still an upward trend there. And in fact, NOAA, I'm talking about the Oceanic Administration, not the biblical guy who probably knew a little bit about sea level rise, have said that 2014 was actually the warmest year on record. So, what does that mean for global sea level rise? Tide gauges have been in use in most ports for over well over 100 years. So if we add sort of mean these have been all mean together throughout the globe. Obviously, the light grey here is levels of uncertainty. Obviously, some of the older records are, there's a lot more uncertainty involved with them. That gets less as we get more modern. And then we can add modern satellite altimetry data onto that. And so basically, since 1900, historically there's been about 20 centimetres of sea level rise in that time. Why is the sea level rising? Again, I'll just zip over the first two of these quite quickly. Thermal expansion. Obviously, when a fluid warms up, it expands, and the Earth's oceans are confined within oceanic basins. So the only way is up with thermal expansion. We all know about glaciers like the Franz Josef here, had a heap more ice in them 100, 200, 300 years ago, and this is happening all over the world. This very fast melt of glacial ice. One of the biggest uncertainties, and why when you see these predictions of global sea level scenarios, and why you hear in the newspaper one scientist says this and one scientist says this, someone says it's going to be 4 metres sea level rise in the next 100 years, and someone says no, it's only going to be half a metre, is because of what's happening, or what we don't quite know about what's happening with the polar ice sheets. And there really is still a great deal of uncertainty about the contribution of ice sheets to sea level rise. So we've got 3 sheets, the one that covers Greenland, and then the 2 in Antarctica, the West Antarctic and the East Antarctic. Now these ice sheets hold a staggering amount of ice, they're many kilometres thick. It's been calculated that if they all melted, which isn't going to happen tomorrow, thankfully, they would raise the global sea level by 63 metres. That's how much material of ice is in there. A differentiation between an ice sheet and an ice shelf. An ice sheet sits on, is a large, obviously, sheet of ice that sits on bedrock, many kilometres thick. An ice shelf is, as the name suggests, a shelf of ice attached to the land, but it floats on water. It's still very thick, but it floats on water. And what the importance of ice shelves are that they are kind of like buttresses or retaining walls to the ice sheets. They kind of hold them in place and keep them stable. What happens when one of these ice shelf kind of runs into trouble and destabilises? This is the Larsen B ice shelf. You may have heard of the Larsen B ice shelf. In 2002, it kind of disintegrated. Now this is the size of Stewart Island. It latches on to the main bit of the continent around about this arc here, latches to the bedrock. And over a period of only sort of 3 months or so, here we go, February 2002, it started to break up. And by March, it was completely broken up. So these ice sheets and ice shelves play a very pivotal but not completely understood role in contributions to sea level rise. So that's a double whammy. There's actually a triple whammy. So we've got ice sheets being affected by atmospheric warming. We've got ice sheets being affected by destabilisation of the breakup of the ice shelves. And we've also got this effect where as the ice shelves break up, this is a satellite image of the topography of the bedrock under the ice shelf, under the ice sheet. Here you can see the dark blue lines as they get bluer. These are below sea level. So what happens is the bedrock in many places is sloping inland away from the sea and below sea level. As the ice shelves break up, this allows some of the warmer water to infiltrate between the bedrock and where the ice sheet interfaces with it. That trickles down, so it melts from it's melting from underneath as well. So you've got melting from the top, melting from below, and melting or destabilisation from the side. And I guess predicting how much and how rapidly each of those ice sheets could shrink in a warming world is a very complex task. And like I said, that's one of the main factors behind the uncertainty and what might happen to sea levels in the future. So like I said, we really don't want to, there's two aspects to sea level rise. There's absolute sea level and relative sea level. What's the difference? Well, the sea surface has a topography, just like the land. The sea has a topography. It's not the same level all the way around the world. And this is the water surface elevation from ocean to ocean. It's got contours. You can map the surface of the sea, and the surface is kind of warped by the gravitational pull of land and ice masses. So, for example, a mountain range, a subsea mountain range, will pull water towards it, creating a bulge in the sea. And ice sheets, for example, because of their mass, it pulls water towards them. So the problem is when those ice sheets melt, the gravitational pull relaxes, so you get this uneven distribution of sea level around the world. And that's measured by satellites. And it's the surface elevation relative to the Earth's centre, or the ellipsoid. So the ellipsoid is just a kind of, I guess, a generalised, perfect representation of the Earth's surface that surveys use. Relative sea level, on the other hand, is the local sea level compared to the land. So that's, we've seen what happens globally, or the absolute sea level, but really we're interested in what's happening to the land. And this information is gathered from tide gauges, from sea level recorders such as our one at Sumner Head. This is a sea level recorder that Canterbury runs in conjunction with NIWA. It's been going for nearly 20 years, and it's that's still very short term, obviously, in the term of sea level. But what we can see from the Sumner sea level recorder, this is just over a week or so. The red line is the predicted tide. The blue line is what actually happened, and the difference is represented in this bottom graph, which is basically storm surge. And I'm going to talk a bit about sea level variations and storm surge and inverse barometer effects in a minute. So back to relative sea level. Relative sea level is affected by land movements, so tectonics and glacial isostasy. So glacial isostasy is basically glacial rebound. Back in the last interglacial, when there was heaps of ice cover weighing the land down. When that ice melted, the land rebounds, and the ice melted quicker than the land can recover. And some of that is, in many places around the world, that's still happening. So, for example, in many Scandinavian countries, or the northern part of the UK and Scotland, we've got the land is still rising due to this glacial rebound. So, in many places, the land is actually rising higher than the sea level. So you've actually got a relative drop in sea level in those places. And obviously, countries like New Zealand are very tectonically active, so that has a really major bearing on how we look at local effects of sea level. Sea level predictions. You might have seen this one before. This gets struck out every 5 or so years whenever the IPCC, International Panel for Climate Change, puts out their predictions. All their sea level predictions are based on climate modelling. So they take their climate modelling and apply that to what's going to happen with sea level by applying thermal expansion formula and the impact of of the warming on glacial melt and ice sheet dramas there. So this is the latest, 2013. It's very much scenario based. So you notice the blue shaded area. This is, essentially the best case scenario. If our greenhouse gas emissions stopped bang right now, this is you're still going to get upwards of 30 centimetres of sea level rise in the next 100 odd years. So even if we stop doing what we're doing, there's still going to be this residual effect of sea level rise to at least sort of 0.3 or 0.4 of a metre. The orange shaded area, note the amount of uncertainty, is kind of that's like a business as usual approach. That's if we just keep going how we're going. This is what the sea level rise curve is going to be. So anywhere up to a metre. NIWA, Rob Bell, in particular from NIWA, has sort of adapted this to kind of the New Zealand situation, and he's saying that we should be really preparing the next 100 years from a 0.7 to 1 metre sea level rise. But there's also, remember, all these uncertainties about what's happening to the ice sheets, and there's since this report came out, there's been a lot of scientists say, well, we think it's a bit low. Maybe upwards of 2 metres is more realistic. What's happening locally? So these are our tide gauge records, mainly at ports because that's where they've been in for the longest. These are separated out for clarity, so don't read into that Auckland is much more trouble than Wellington. These are all fairly relative. So if we average them all out for New Zealand, our trend, the relative trend, given into consideration, movements of the land, trend is for has been since 1900 1.7 millimetres a year, or 17 centimetres in the last century. The Christchurch, or more correctly the Littleton rates, are a little bit higher. We're looking at 1.9 millimetres per year since 1900, so 19 centimetres. The thing to note really is this upward trend. There's no real, until about the last, if you really look closely at the last sort of 10 years of data, it's been reasonably linear. There's been no evidence of acceleration. And also note that there's variability, a lot of seasonal and annual variability in this record, but still with that trend. So I'd like to talk a little bit about that variability, because as we all know, a base rise in sea level doesn't really create any new hazards. If we're talking about coastal hazards, it really just exacerbates what we've already got. And the coastal hazards that we've already got really revolve around variations in sea level. So these shorter term variations. Global circulation cycles like El Niño southern oscillation have an effect on our local sea levels. La Niña conditions, our one on the right hand side. Westerly winds push warm water across the Pacific into the Western Pacific, and that has the effect of raising sea levels slightly in our neck of the woods and reducing them over in South America, and that causes upwelling of colder water, depression in their sea levels, but also a very good crop of anchovies. And in the opposite cycle, in the El Niño, when these westerly winds break down, the water sloshes back eastwards across the Pacific, so we get a reduction in water levels in our neck of the woods, and South America gets an increase. Now, conservatively, that occurs on a kind of 2 to 4 year cycle, but that's the strength of El Niño Southern Oscillation does vary a lot, and it also varies a lot on another scale, on a 20 to 30 year scale, and that's called the Interdecadal Pacific Oscillation. So the strength of the ENSO cycle fits in with another global circulation cycle on a 20 to 30 year basis. And what that all means really is that the variation in New Zealand due to these ENSO and Interdecadal Pacific Oscillation is sort of plus or minus 25 centimetres. So that's a half a metre range. Tides, obviously, are another thing to plug into sea level variation. Tides vary a lot across a month, as you all know. This is from NIWA's Tidal Predictor, just looking at a month over a month in 2014. So what you immediately see is these, what we all know as fortnightly spring and neap tides. Spring tides occur when the sun and the moon are in alignment, so their gravitational pull are sort of combine to cause a great pull on the Earth's water surfaces. So we get much higher tides. In converse, much higher tides and much lower tides. And neap tides are when the sun and the moon are in opposite axes to one another, so their gravitational pulls kind of work opposite, work against each other, and we get a smaller range of tides. And that's kind of the textbook definition, but what we've got in Canterbury is an extra layer of this tidal influence, known as perigee and apogean tides. Because as the moon orbits the Earth on its monthly cycle, it's an elliptical orbit, so when it's at its perigee, it means it's actually closer in its orbit to the Earth, and when it's in its apogee, it's further away. And so we get this monthly variation in tide as well. And when you get this perigean tide, so a tide when the moon's closest to the Earth in its orbit, and if that combines with a spring tide as well, you get these things known as perigean spring tides, also known as king tides. So whenever you see, in the media, lots of coastal flooding, the slide I had of the Auckland motorway in 2011, that was a king tide event. So they're the ones that generally, if you see a news article about coastal inundation, it revolves around one of these perigean spring tides. Another major variation of sea level is weather-induced. So obviously, when we have either an anticyclone or a cyclone over the surface of the sea, that has an effect. A high-pressure system, big heavy weight of air on top of the ocean helps push the sea level down. Conversely, when a low comes over the country or over an area of ocean, that pressure is released, so the water level rises, a bit like a waterbed, if you like. If you want to use that analogy, you push down on a waterbed, and let go, all the water comes springing up. And this is known as the inverted barometer effect. So generally, a 1 hectopascal drop in the pressure will result in a 1 centimetre increase in sea level rise. So in our example here, we've got a low pressure system of 992 hectopascals and a high over in Tasman, 1024. So really the variation in sea level on those two pressures would be upwards of 32 centimetres. We've also got wind setup and wave setup. So wind setup during a coastal storm, for a southerly, for example, in our situation, strong winds blowing onshore, that sets up the water surface as it pushes up against the coastline. And wave setup is the effect of waves breaking in the surf zone, also raise the level of the water. So an inverse barometer plus wind setup plus wave setup is what we know as storm surge. And you can add to that variation in storm surge as wave runner. So obviously the bigger the wave, the more wave runner we're talking about. So put that all together. The summary: storm surge. So that's your inverse barometer, your wind, and your wave setup. Add that to the tide, and you've got a storm tide level plus your wave runner. Add that to a base level rise in sea level. You can figure out what the effect is going to be. What is that effect? We can look at this on a number of scales. Coastal responses to sea level rise and sea level variability do vary over a time scale, but the important thing to remember is that coasts are incredibly dynamic. They're not going to just sit there and let sea level rise happen to it. They're going to respond. Obviously, most coastlines, or unconsolidated coastlines, sandy coastlines, gravelly coastlines, are able to move vast quantities of sediment around, onshore, offshore, alongshore. They're just not going to sit back and let sea level rise happen. They're going to respond, and that response has an effect on us. On a larger scale, what we've got here is some old Christchurch coastlines throughout the Holocene. So the Holocene is the last sort of 12,500 to 13,000 years. So the time since the last glaciation, our interglacial. And during the last interglacial, sea levels were a lot lower than they are now, up to 130, 140 metres below where they are. So 8,000 years ago, the Christchurch shoreline might have looked a little bit there, and as sea levels rose through the Holocene, they reached a transgressive maximum of about Riccarton, so not far from where we are now. And then as the sea level stabilised over the last 6,500 years, the shorelines built out. Here we are 2,000 years ago, and we've also mapped in the current shoreline here. So the thing to get out of this is that 1,000 years ago, this part of Christchurch didn't really exist. The spit and this coastal area is very, very new, and it still has a lot of changing to do. The other thing too, important thing too here is that this is a Holocene coastal plain. These are all marine deposits. So if we dig down anywhere east of Riccarton, we'll find marine deposits. And we all know what marine deposits and river deposits do when they get shaken up. What are some of the other responses? Looking at a bit of bringing the scale down a bit. What are the effects of sea level rise on our, for example, on our rivers, estuaries, and groundwater systems? We start with groundwater. Groundwater slopes down to meet sort of the mean level of the sea. We raise the base level of the sea. The groundwater level was going to respond and rise in response. Obviously, on a Holocene coastal plain like Christchurch, we're going to have to be more susceptible to the effects of liquefaction, for example, from earthquakes. So we're entering into a multi-hazard perspective here now too, where it's not just sea level rise affecting coastal hazards, we're affecting other hazards as well. Rivers are the same. Rivers run down to meet the coast. The rivers are going to, with sea level rise, the rivers are going to reduce their slope, and that's going to have an impact on sedimentation and drainage issues. Here's some mapping that Tonkin and Taylor did on around the Christchurch area, potential effect of estuaries, around estuaries and the river systems. The light blue is the spit here. Here's the Avon River and Heathcote The light blue line is what we could expect for a river and estuary system, for a river and estuary system with a 1 metre sea level rise. And the dark blue line is looking at that same 1 metre sea level rise with a 1 in 100 year storm tide with it. So we're not looking at small areas that will be affected with a 100 year sea level rise of 1 metre. How much time have I got left, Brody?
It's about 5-10 minutes max.
The other thing that happens in the sea level rise is it impacts the tidal range and frequency. So as sea level rises, it increases the relative frequency of high tides that will exceed a given level. And this is a plot put forward by Rob Bell from NIWA, just to demonstrate this fact. This is a high water range from Tarakohi, which is Golden Bay, I think. And so this is the maximum range of high water. We have a level of, so remember these very high tides, mean high water Erosion spring tides. Current sea level, that level is only going to be exceeded 3.5% by 3.5% of tides. As we progressively increase sea level, we get a progressive increase in the frequency of that same level being exceeded. So with a 0.6 metre sea level rise, those tides are going to be exceeded 50% of that time. And that's even exacerbated more on the Canterbury coastlines, where we've got a much smaller tidal range. Here's an example from Kaikoura. We've got our mean high water spring, Erosion spring tide is exceeded by 10% of all tides. And it only takes just under 20 centimetres of sea level rise for that level to be exceeded over 50% of the time. And 100% of the time, not much more than that. Estuaries will respond by, obviously, shorelines will erode. We get coastal squeeze. Coastal squeeze is if there's if you've already got some coastal protection in place, like a stop bank. As the sea level rises, there's nowhere for the shore to move back to. You get a squeeze of that zone, losing all those ecological values on the estuary margins. And the earthquakes in the estuary have given us a really good laboratory, I suppose, to see what's happening there. And here's an example of this. This is just around the South Brighton Domain. This is a Gabion, much loved Gabion seawall, revetment. This would have been designed, obviously, to withstand some of the highest tides, but with about 0.5 metre of subduction subsidence of the middle of the estuary. We now get consistent erosion back over that wall. The responses on sandy beaches. Won't have time to go into this in too much detail, but again, sandy beaches will respond by moving sediment around. There's a thing called the Barone Rule, which essentially says, it's a theory, and it's much used and much misused, but the theory is that it says if you get a sea level rise of X amount, you get the beach profile will erode backwards, obviously, but build up. So the material will be eroded from the top of the foreshore. Some of it will be deposited down on the near shore, which will be about the same amount as what level of sea level rise we have, and then the back shore will accrete. And Totten and Taylor, in that same 2013 report, applied the Barone Rule to the Christchurch coastline and got an estimate with 1 metre of sea level rise of a retreat of our dune systems by around 60 metres. But you may ask, we've had we've had sea level rise over the historic record, 20 centimetres. why have we not seen that erosion on the Christchurch coastline? Because our records show that the Christchurch sandy coast has been, over the last at least century or so, has been very stable, if not slightly building out. Why is that? And that's the limitation of the Barone Rule, in that it doesn't account for any sediment inputs, or it doesn't allow for the impacts of wave climate. So what's happening along the Christchurch coastline is that we're getting enough sediment coming in from the Waimakiri River. We're getting enough shelter from waves from Banks Peninsula for the coastal system is keeping pace, or even keeping slightly ahead of what's been happening historically for sea level rise, which is a good thing. The thing that, and it's currently awaiting public release at the moment, Tonkin and Taylor have had a bit more of a think about what that response might be in terms of when might that flip, when might we get a change from stable coastline to erosive coastline based on future sea level rises. So watch the space for that. I can safely say that that 60-metre retreat is probably a little bit on the drastic side. And just finally, one of our other major forms of coastline along the Canterbury coast are mixed sand and gravel beaches. Now most of these are already eroding at a reasonable rate, 0.5 metre to 1.5 metres a year, depending on where you are. Beaches such as the Washlight barrier at Timaru, Washlight and Seadown, and these are at the moment responding to that historic sea level rise. So these erosion rates are essentially building in what's that 20 centimetres or so of sea level rise over the past century. Now why these coasts are susceptible to sea level rise is that the way that they erode is through rollover. So when you get high seas, the waves wash over the top of the barrier. This is the Wainona coastline south of Timaru. Here's the Wainona head arm. Water washes sediment over the beach, and the beach translates shorewards by that erosive process. And why sea level rise is important for that? You get a rise in base sea level. You're going to get more and more. Remember those graphs. You're getting more and more frequency of tides and storm tides reaching that level, exceeding that level, and pushing more gravel over the back. You're also getting an increase, and this is important for some of the low-lying areas, particularly in South Canterbury and at river mouths, an increased amount of flooding. Increased overtopping is going to increase your flooding potential and your flooding frequency. And there's a model that we can apply to these gravel barrier beaches. It's sort of a modified Barone equation. Don't worry about it, but the end result, if you plug in all the numbers, we're probably going to get an additional, with a metre sea level rise, you're going to get an additional erosion rate of 0.2 to 0.5 metres per year going forward. So we're going to increase, some of these erosion rates are going to increase, from, up to 1 to, the real quick erosion rates are going to increase even more, potentially up to 2 to 2.5 metres. And finally, unconsolidated cliff-back coasts are very sensitive to sea level rise. These Lurse cliffs south of Timaru, also our alluvial fan cliffs, last slide, Brody, are going to be very susceptible to sea level rise. As sea level rises, the only thing that erodes these cliffs are coastal processes. So again, more frequency of tidal exceedances, the narrowing of the foreshore, which is really the only thing that protects these cliffs. So you get a narrowing of the foreshore, more and more occurrences of these cliffs erosion. So the erosion rates on these cliffs are going to ramp up as well. I'll leave it there.
Great, thank you. Okay, we've got a good 5 minutes, or slightly more than 5 minutes. So, questions. Surely we've got some questions about all of that. Who's first? G'day.
Well, most of your focus has been on coast Because most of the time in the Tidal report was focused on Avon and Heathcote.
Yeah.
And of course, as the erosion and as all that happens, then the Avon and Heathcote are going to be overflowing. And admittedly, that's not our river, so we're not quite so concerned about that, other than we might have houses there. But that is probably the biggest concern with Grocery City Council, and I don't have an answer for it.
Yeah.
I guess just sort of getting coming to make about the river impact.
I mean, you're talking in terms of management of those effects?
Or just the severity or anything else?
Yeah, well, those flooding maps that I put up are kind of a first, Clog and Taylor did a first cut of that. So that's been, you know, in the most, there's a recent report sitting at the council waiting for public release. I think they're figuring out how they're going to break the news to everybody. That does show that, you know, that's not far off the money, and those maps are going to be used in the city plan review. So those floodable areas are going to be identified on limbs, planning documents. You know, and I don't know what rules are going to be associated with those yet, but they're certainly taking it very seriously. That's for sure.
Waikuku Beach, that area seems to be, the 4 dunes are getting a hammering at the moment.
Yeah.
Is that going to sort itself out? There's a lot of questions from the locals because there are now pine trees which haven't seen any sea level at all now falling in the water or about to.
Yeah, no, I mean, these things are the cut and fill cycle of general coastal processes, you know, do occur, and you know, generally beaches will recover from that process. You're talking a bit further up the riverside. Actually, at the beach. Yeah, that's interesting.
Right through the ends. Okay. The 4 dune is quite steep.
Yeah.
It's taken
yeah, we obviously have had, you know, over the past fortnight or so, we have had some big tides and some associated with some big seas and some good storm tide. But I think that, you know, those are short term erosion. I think that they'll recover in time. It doesn't happen quickly, and it does cause a lot of concern when people see that not happening quickly. And a lot of that's to do with the vegetation on the sand dunes as well. You know, if that takes a battering too, obviously it takes a lot longer to recover.
Justin, there's a whole lot of suite of responses to sea level rise. Can you just talk about some of them that are open to us and to other TAs?
Yes. I guess from the planning responses, we have hazard zoning, which takes into account not only, well, it has to take into account not only sea level rise, but any short-term changes or long-term. Short-term changes in terms of what, you know, what Simon's just pointed out, in terms of the, you know, short-term cycles of erosion and recovery, as well as the longer-term processes, whether your shoreline is, you know, stable in the long term or eroding in the long term, and then the impact of sea level rise, such as applying something like the, you know, profile response model. You can add all those up and to get a zone that you can, you know, apply to. Apply to planning documents. Obviously, you know, the word that no one likes to hear is sort of, you know, the planned retreat approaches, engineering approaches to, you know, from seawalls to more softer, you know, dune restoration programs. You know, you can go the Dutch option of dikes and tidal barrages. Expensive options like that. Yeah, no, I mean, I could talk a lot about, you know, various options. There's many out there. But, you know, it's going to, the time is coming for some hard decisions on that, because that eastern part of Christchurch is going to be half a metre sea level rise, probably at best. There's not. That's going to happen, and so there's going to be some decisions to be made from a planning perspective.
We hear a lot about the biodiversity value of coastal lagoons and hapua. What do you think will be the ultimate outcome of the interaction between some of our big rivers and coastal erosion at the river mouth, and even Te Waihora as coastal erosion? Have we got any data about that?
Yeah, well, I mean, we've got some very good data about some of the South Canterbury coastal lagoons, such as Wainono and Washdike Lagoon, for example. The erosion over the past sort of 150 years has reduced the area of the Washdike Lagoon through that rollover process by 250 hectares. So you're losing a lot of ecosystem there. Like I said, those sort of coastal lakes and coastal hapua are sensitive to sea level rise, and that they depend on their levels are dependent on the sea level, so they keep track with sea level rise. So the more frequently they're overtopped and washed back, those areas will shrink over time. I think the coastal hapua, for example, where you've got that interaction of river mouth dynamics, so you've got the fluvial impact and the coastal impact. I don't think we're ever going to lose that system, but there is evidence that some are becoming much narrower. You're always going to have that, the offset of the river mouth churning out the back shore. So I don't think you're ever going to lose those environments, but certainly there is evidence that some of them are shrinking in size.
Obviously, science has been able to fine-tune its predictive tools around this, and we're now able to estimate average rates of change or loss better than we were 20 or 30 years ago. But I wonder how good we are at providing tools for the here and now. I was just looking at your picture of the train there. Can we give reassurance to the chair of New Zealand Rail that he's got another 5 years, or should he be buying that property behind the tracks now?
Kiwi Rail had a really good response to this, and that they just dumped about a football-sized field amount of rock just in here to hold that back. But I mean, there is Kiwi Rail's a little bit they're quite strapped for cash, so they're aware of some of the issues down here, and I think they're a bit more. They have to be a little bit more reactive to some of the changes they make. But I mean, what was your question again?
I just wonder how good our tools are at predicting, the rate of loss in a specific situation like that.
We need more resources on the coast.
I mean, that's something that we are. That sea level rise. The response of coastlines to sea level rise is certainly going to be a big thing that we're going to look at in the future. That's on the cards for us to look a lot closely at. I want to see what comes out of City Council's Tonkin and Taylor report to see if that's applicable to other areas. And it's I've read it and it's pretty good stuff. So so I think that for other districts they could apply some of that in terms of if they want to look at what they do for hazard zones, for example. I mean, we are in a fortunate situation in Canterbury, realistically, that I mean, apart from the urban Christchurch urban area is where we've got like lots of erosion. There's not a huge, there's not, Tawanui and Matarangi are not not going to fall into the drink. So I mean, there's still a lot of economic loss potential in terms of eroding of valuable land, or particularly saltwater inundation and flooding of areas. But I mean, that is going to be a focus for the next few years. I think that we'll need to look at a bit more as applying some of these predictive tools. Probably about 15 years ago, we set out applying a lot of sort of coastal shoreline modelling techniques. There was quite a few reports, Thompson and Taylor and Derek Todd did quite a lot of work applying. At that stage they were fairly newfangled models, and what we found that we didn't really have enough was the classic information going in wasn't particularly flash. Like we didn't have a wave buoy record, for example. We didn't know what the waves were doing. We didn't sea level variability. The sea level recorder had only really just gone in, so we didn't really have that information. But 20 years on, we're starting to get together a lot more valuable information, as well as 20 more years of our physical coastal surveying data, which concentrates a lot on this sort of short-term variability, which is very important in some of these response models. So we're getting to the stage where we can be a lot more confident, I think, in some of the predictive tools.